Hello, everyone. Welcome to Foresight's Molecular Machines group. Today, we're so happy to have Anna Balazs here with us today, and she'll be discussing fluid flow machines from the University of Pittsburgh. So thank you so much, Anna.
Thank you, Lydia. Thank you for the kind invitation. I would like to talk to you today about chemically generated fluid flow machines and how you can use them to autonomously assemble hierarchical, these are hard words, hierarchical 3D structures, but they're written down so you can see this. And this is going to be a computer modeling talk. And yes, these are lovely examples of things that I'll show you. This is one of hierarchical assembly where the fluid does the work. And this is a Mandela pattern. And again, it's these posts that I've arranged, and it's the fluid that's doing the work of generating the pattern. So I have to tell you the lovely people who actually did the work, and their names are on the bottom, Abro and Oleg and Aslam. So I'm the spokesperson for their really lovely work. So I'm sorry, I've just talked a little bit by stuff on the top, but it's all good. So all of this builds on, and I think you've had a Yushman Sen talk in your series, and a Yushman Sen found that nanoscale enzymes in solution can generate these fluid flows, and the fluid flows are quite extensive. And so he's looked at, and we both did, this is a paper we wrote jointly, with a centimeter size object, and the fluid flow generated by the nanoscale enzymes is sufficient to generate the flow to move this around. So that's really exciting. But the question you have to ask is, how can I pattern the flow to get it to do what I want? How do I pattern the flow so that I can manipulate objects in solution, I can form these 3D structures, or I can get hierarchical structures, just like the ones you saw at the beginning. And so that's the challenge. And so the key is this chemically generated fluid flow. And I'm going to tell you two stories that have to do with that. And one is going to be assembly of 2D mobile sheets into 3D macrostructures. And the fluid's going to do all the work. And the other one is organizing posts into 3D macroscales. And one of the really fun things about that is I'll show you that the posts leave a unique fingerprint reflecting the chemistry that's going on, and that these can act as sensors. So this is all without external power. The only thing is a little drop of chemical to initiate the process, and then it spontaneously occurs. So how is that? How could that happen? Well, when you have a reaction, and this enzymatic reaction, catalytic reaction, almost any reaction, you take reactants and you convert them to products. Now, if the reactants and products don't have the same volume, then there'll be a density gradient in the fluid. If there's a density gradient, then that imposes a force on the fluid trying to get rid of the gradient. And the force then acts on the surrounding solution. And every story I'll tell you is a confined fluid. So they're in a confined box. And so when it imposes a force, fluid doesn't have too far to go, it can only go up to the top, around the sides, and along the bottom. And so it creates these beautiful vortices, and it's those vortices that I'm going to use and pattern to make the designs I'd like. So in this process, and this process is called solidal buoyancy, it might look familiar in terms of thermal buoyancy, but here the buoyancy is due to these density gradients. And if the products are less dense than the reactants, then you get inward flow, which is the object on the left. But if the products are more dense than the reactants, you get this outward flow. Let's go back to the inward flow. This is very much like thermal buoyancy. The less dense fluid rises to the top. It's in a confined chamber, so it has to come back down around the sides. And here, if the product is denser than the reactants, then it first comes down and hits the surface and then has to recirculate. So the critical number, the dimensionless number that characterizes the system is called the Grashof number. And the critical parameter is called the beta, is beta. It's the solute buoyancy coefficient. And that tells you how much the volume of the solution has changed from pure water when you add these reactants. And so we look in the range of Grashof number 100, 200, and fluid velocities are, fluid velocity that is sort of like in the microfluidics range, they're microns per second. And the Grashof number tells you something really important because the Grashof number is proportional to the velocity of the fluid, and you can change the velocity of the fluid by varying the height of the chamber. So, is this real? Has anyone ever seen such a thing? Well, there was a really beautiful paper that came out in 2019 where they showed the effect of solute buoyancy on yeast cells. And so yeast were sitting at a air-liquid interface, so air is a fluid too, and they take in nutrients and they make waste. And the density of the molecules that are the nutrients and the volume of the molecules that are in the nutrients are not the same as the volume of the molecules that make up the waste. So they generate these wonderful currents, which you can see on the left-hand side, where it says metabolically induced flow. And so they're really using this difference in density caused by the nutrients and the products. And there's a micrograph of the generated flow. And you think, well, why is this beneficial? It's extremely beneficial if you want to take over the world. So if you have one large colony, and then this fluid flow sort of rips it apart into smaller colonies, then each colony can keep growing until the same process happens again, and you can just spread out forever. So it's a very useful evolutionary phenomena for taking over space. So we're going to use this solute buoyancy phenomena. And as I indicated, I'm going to tell you two stories. One is the spontaneous self-assembly in 3D, where I put the sheets, they're 2D sheets, and I put them on a surface, and the fluid just pushes them together so that they come together. And then furthermore, it propels them upwards to make a little box. And that's the story I'll start with. So this clearly involves formulation of new models, and that's what we do for a living. And I have to be able to model the sheets. Those are the things that are going to be moved around by the fluid. And so the elastic sheet is just interconnected mesh nodes. They're Kirchhoff rods. They have a bending modulus. They have a stretching modulus. And they also feel dynamic forces and gravity. There are fluid structure interactions because the fluid is going to hit the sheet, and then there's conservation of momentum. So the sheet hits back on the fluid. And then the sites, which are drawn in blue here, there's a steric repulsion between them, so they don't lie on top of each other. And that's just a Morse potential. And there's a steric repulsion between them and the container, the sides of the wall. So this is the essence of the model. So remember the ingredients. I have fluids, I have flowing fluids, I have chemistry going on, I have reactions going on that are generating the fluid flow. And then in some cases, I'm not sure I'm going to talk about it today. Yes, the sheets actually undergo macroscopic motion. So the first equation is the continuity equation. The second is the Navier-Stokes equation, which we use the Lattice-Boltzmann formulation. And F is a body force. It's the body force from this solute buoyancy effect. And this is the equation just telling you how the chemical concentration is varying as a function of time. And then this is the equation that tells you, in addition to all that, the sheets are moving too. So all those equations have to be solved simultaneously. And we can do that. So the other thing is the reactions. How do I model the chemical reactions? Well, I use the most primitive version of catalytic reaction. It's the Michaelis-Menten reaction rates. And those are very well known for catalytic reactions. So those are the ones I use. All right, so I have to prove to you that this model has some validity. And not only can it be applied to sheets, but obviously, you can break the sheets down into little particles. And so we've used it to look at particles. And this is a scenario where we looked at a particle that's completely coated by catalyst, by enzyme, and we give it the reactant and the product, so that the red one is active. So that actively generates a fluid flow, but it imposes a drag on its neighbor when its neighbor is passive. So the neighbor is passive, the red one is active, and you can see they move little dimers. So there's this very beautiful paper that came out after that by Ray Capral, and he looked at photoactive particles. And when the light is on, you can see, can't use my finger really, you can see that the black sphere and the white sphere make a dimer. And then when the light is turned off, they move apart. The black sphere is the one that's active and the white one is passive. So we see the same thing that, luckily, that was seen subsequently in experiment. And this was this nice experiment that we did with Ayush and Sen, where we had these rotors, and these were just thin plastic sheets, and they were coated with different enzymes. And depending on if the enzyme gave you outward flow or inward flow, then I could get it to rotate clockwise or counterclockwise. And so you saw the movie, and the bottom are cartoons from the simulations, and above that are the actual micrographs. And so we got very good agreement. We have tested this model quite rigorously, luckily with this amazing collaboration with Yushman, and also with Howard Stone, who's truly amazing. So not only did the comparison help to calibrate the model, to validate the model, but it also helped to get the critical experimental parameters that we needed and to calibrate our simulation parameters to the physical system. All right, so now remember, my aim is to design a fluid flow, design a scenario so that the self-organization is going to occur by itself. It's a dynamic self-organization. And so it's going to be 2 stages. I'm going to put the sheets around a central pad sheet, and that central sheet is stuck to the surface. And in the first stage, then, because there are enzymes, and the enzymes are on the central sheet, they're the balls in black, and they're only on the central sheet. So when I add the reactant, that starts an enzymatic reaction, that generates a fluid flow about the enzymes, and that pulls the other sheets together. It's a fluid drag. It's a drag acting on the other sheets, and it pulls them together. But I would also like to make a box. And so after the sheets are pulled together, there's sticky bonds, it's functionalized sites on the sheet that bind to each other. Easy to do experimentally. So they bind together, and then that fluid flow persists because I still have the enzymatic reaction. And so it drags it upwards spontaneously, makes a box. And the reaction that we're looking at here is catalase. So catalase takes hydrogen peroxide and decomposes it into water and oxygen. So on the left is I've put a triangular base, and then I have these square sheets, and they're going to make a prism. And on the other hand, I have a triangular base and triangular panels, and they make a more tetrahedral type of object. Now oh, really? No. Yes, watch. So honest. This is quite remarkable because not only are they assembling, but if you look carefully, it's 2 different symmetry groups at the same time. So, you have the triangular one, the tetrahedron, and you have a prism. And the right components are going to their right partners. So I can do simultaneous assembly of these complex geometries. And why would I like to do that? Well, I can dynamically reconfigure the surface before it's reconfigured. It's just flat. So if I shine light on it, it'll give one optical signature. But now that it's reconfigured and it has these bumpy bits, then it'll give another optical signature. And these bumpy bits I can make ordered so that I get a very specific signature out of the material. So that's cool. But it doesn't always work. So I've told you everything now about buoyancy effects, but sometimes I have to call in other effects. Other effects create concentration gradients, thermal gradients, and I have to be able to use those as well. And so I'm going to use diffusioosmosis, and that force that's generated is proportional to concentration gradients in the chemicals. And the really beautiful thing about diffusioosmosis, it happens primarily at surfaces. So you can localize that force near the surface, whereas pseudobuoyancy is a bulk phenomenon. It travels throughout the chamber. So I have a way of tailoring the top and tailoring the body of the fluid. And then I can make boxes. I can make boxes and close the lid. And it's the sort of buoyancy that's pulling the boxes together, but it's the diffusioosmotic phenomena that's letting me close the lid. And again, one thing that's really nice is that these phenomena are independent of each other. Remember, sort of buoyancy is dependent on density. Diffusioosmotic forces are dependent on gradients in chemical concentration. So I can manipulate them independently, so I can get them to localize this. Just fold the top of the box, please. You might ask, and it's a very good question, well, that's nice, but how fault tolerant is it? And it's actually quite fault tolerant. So we did measure that, and we had put it in the configuration that you can see on the top. And we varied the angles relative to the main axes of that configuration. And we found that if you have a 10% deviation in any of those angles, the method is still quite robust. And then we also said, well, what happens if I take out some of the bonds or I take out some of the catalytic sites? And so normally there would be, if it was a perfect system, there would be 12 red bonds between the catalyst sites, which are in blue, and the inactive sites, which are in green. So we took out half. And then we took out some of the catalyst as well. So 9 and 10 have the catalyst removed. And even with that level of non-uniformity, we find very good self-assembly. Those numbers are pushing the limit. I mean, I think I take out more than 50% of the bonds, then I don't get the nicely directed self-assembly. I could probably reduce the amount of catalyst, but it's really, I need a large fraction of those sticky bonds to be present. So if I know how to do that, then I should be able to now come up with a way of making, not just closing the box, but then adding another component to the box that can have some function. And here's what happens. So on the left was the box, except the box is decorated with antennae. So it's supposed to look like that little insect on top. So the box comes together and little antennae stick up in the solution and they start rotating because of the fluid flow. And I can make the antennae sticky so that they'll collect particles in the solution, collect particulates, collect pollutants. And so that this lovely little creature that looks very much like that object, of course it does, is created through one self-assembly step. And I remind you, if I didn't make this clear, that these are centimeter to millimeter size objects, millimeter to centimeter size objects. So this is macro scale, motion on the macro scale generated by these enzymatic reactions and the fluid flow in the confined geometry. Another nice toy you can do, another nice advantages of this, is you can assemble the tetrahedra by themselves. So I have 2 nice tetrahedra. And then I can allow the 2 tetrahedra to come together and form a more complex structure. And this is very nice because the alternative to some of these things is this kirigami and origami. But with kirigami and origami, once you've made the structure, you've made the structure. There are very few ways then to do the next step where the objects that you've made are driven by themselves to organize into larger structures. And this has that ability. Are there materials that could do this? Well, yes. And the way we know this is because I have a wonderful collaborator, Todd Emmerich, and all I have to tell Todd is the equation for the Grashof number. I have to tell him what my range is. I have to tell him that it's 2 times 10 to the second. So I'm in the range where pseudo buoyancy dominates over viscous effects. And again, beta is that coefficient that tells you the difference in the volume of the fluid with or without reactants. And the bottom part is the viscosity coefficient. So this says buoyancy is much more important than viscous effects. And I can also calculate the flexural rigidity that I need for the forces to be effective on these sheets. And we did that. And lo and behold, Todd Emmerich can make materials that would satisfy that criteria. You can connect functionalized objects in an oil-water interface and then polymerize them. And also he's done that with Count P mosaic virus. So materials exist to actualize this. So now I'm going to tell you the second story, where in the first story, everybody was mobile, could move except the center bit. And now everybody's going to be immobile. So these are posts, and they're anchored to a surface. They're also on the millimeter to centimeter size scale. And if you look carefully at example 2, you'll see there's a dropper adding fluid, and you'll also see there are a number of different catalysts. So there's enzymes. So there's catalase, and there's urease, and there's acid phosphatase. And the really beautiful thing about enzymes and catalysis, there are probably many very beautiful things about them, is they're highly specific. The reactions can only be activated by particular reagents, and we use that in what follows. And I'll tell you what follows, but this also has a really nice biological analogy. So this continues to be an unresolved issue that nodal cilia help define the left-right asymmetry in the body. And no one really quite knows how they work. But there are 2 kinds of cilia that participate in this left-right asymmetry. There's the active ones that generate the signal. And then there are passive ones. The active ones are in green. And then there are passive ones, they're immobile, that respond. They have their mechanosensors, and they respond to the signal. So they also show beautiful non-reciprocal motion. And can I generate similar behavior in a synthetic material? But first I'll show you, here's what the nodal cilia look like. You see, some of them are doing these beautiful large-scale motions, and others are going, I'm too tired. So you see that diversity of motion. It's that diversity of motion then that says heart goes this way and kidney goes that way. And all right, so that's what I'm after. Can I make an array of cilia such that one makes very active motion and the other one, a neighboring one, has just standstill? And the answer is yes. So I'm going to explain this box again. So these are anchored cilia. The height of the box is 1 millimeter, but I could look at taller boxes. You have dimensions there. And catalase, which decomposes hydrogen peroxide, is in blue, and acetate phosphatase, which decomposes a word I can't pronounce, but another reactant, And then there's urease, which is activated by urea. So I have all of these present, but I'm going to add the different reactants sequentially. And so if I add hydrogen peroxide, it's only the catalase that's activated. If I add PNPP, then it's only the acid phosphatase. And if I add urea, it's only the urease. So this one system can make multiple patterns. But I think what's even more exciting, and I cannot prove this, it's probably impossible to prove, that it makes a unique fingerprint. It's very hard to prove uniqueness, but you might understand it again looking at the Grashof number. If there's anything that changes in the system, like the height of the box, the beta, the sort of buoyancy coefficient, and beta's unique to a chemical constituent, then I get a very different pattern. So that the pattern you see is indicative of what conditions you're using that happens to be a unique pattern. And it forms a fingerprint. Now, I remember I said I added them sequentially. Well, there's another way I can play and make other pretty patterns. I should just say that I'll also get another really pretty unique pattern if I add them all together at the same time. But let's play with adding them sequentially. And then I add the reactant that excites the particular catalyst, and it makes a pretty unique pattern. That's what I claim. And then I wait till that catalyst and all that reactant is consumed. Then I add another reactant that excites another catalyst, and it forms its own unique pattern. So as a function of time, as you add them sequentially, then they form a kaleidoscopic pattern. It's actually quite beautiful to watch. I don't think these are movies, but what the idea is that the Mandela picture on the bottom left eventually morphs into that picture on the bottom right. So how is it that we can make these beautiful patterns? There have to be some design rules, and yes, there are. And so we need something like the equivalent of a dipole. And so I need my basic fundamental unit is going to be a pair of enzymes where one is the pusher and the other one's a puller. Those words aren't that important, but where one generates inward flow and the other one generates outward flow. So the pusher pushes the fluid away, that's inward flow, and the puller pushes the fluid towards it, and that's outward flow. So if I use these as my basic design motifs, then I have rules for where I can put them to make the pattern that I'd like. And so this was the Mandela, and we arranged the blue is the pusher, and the pink is the puller, and that's the pattern we arranged them in. And then we added the two reactants that trigger this enzymatic reaction, and then that's what gives you this beautiful pattern. And I was fascinated by takes a little while to work. I was really fascinated by the Mandela pattern, and I thought it was sufficiently complex that if we could make that, then that would be showing something. So a Mandela does have a particular requirement, structural requirement. You have to have a square enclosing a central circle, and then you have to have 4 gates. And if you look carefully, then eventually you see the central circle. You see a square enclosing that central circle. And the gates, we're calling gates, are those other objects near the middle of the circle. So we have those design rules. Now that was really fun for this steady state, but the dynamic behavior of these systems is also really fun. So I'm going to have the catalase, and I'm going to add hydrogen peroxide, and I'm going to have one passive pillar. It's not coated with anything, just one passive pillar. And then I see that I get this really beautiful motion where the passive pillar, now, it's looking very much like the nodal cilia, where the active pillar is standing straight, but the passive pillar is responding to the fluid flow generated by the active pillar, is doing this oscillatory motion. And the motion is non-reciprocal. You can see that on the left. So the forward motion is not the same as the back. That's just following the tip of the active one. And why is this working? It's working because, look, the catalase is right in the middle. So it feels a different fluid flow, and I'll show you another picture, than the passive one that's near a wall. So you've broken the symmetry in the system. They feel different fluid flows, and that's why this happens. And I think you see it very nicely here. The catalase is the blue one in the middle, and it's generating this flow field that's symmetric about itself. But the passive one feels that fluid flow, and then it feels fluid flow from the fluid that's reflected from the wall. So that there's an inherent asymmetry in this system. Look at that across one diagonal, the flow profiles, these are very different. And so in this one, we have the passive that oscillates and the active one that's stationary. So there are two interesting things about that. One is that you can get two modes of motion at the same time, and the other is this really is quite like nodal cilia. So I showed you one where the catalase was in the center, and the passive one did this beautiful oscillatory motion. But its motion depends on where I put it in the box. Because remember, I said it was affected by the sides of the box. So you can map out what kinds of motion you would get if you put the passive one at these different positions. So these plots are just one passive one put at different positions, and you can see that you get oscillations like I showed you, or damped oscillations, or highly damped oscillations, and unstable behavior and stable behavior if you put them at different locations. I know this map is a little hard to read, but the star indicates what position you would get oscillatory motion. If I put them there, they'll oscillate. If I put the stable one, if I have a stable one there, then it'll form a stable morphology, stable kind of rotation. It depends on the length of the cilia, and it depends on the mechanical compliance of the cilia. So you need a certain rigidity in your cilia for the trick to work, because if it's too soft, then you'll see the poor little thing, it just keeps banging into the surface, and it can't undergo this beautiful and oscillatory behavior. So it is also dependent on its mechanical properties. And this is really interesting to me. I'm getting close to the end, because I would like to show you that these inactive objects really communicate with each other. So I have one catalase in the middle, and then everything that's labeled P is passive. And I'm moving around. I think I'm keeping P1 fixed, but I move around the others. They're sort of gauge bees. And I look what happens when I move them with respect to each other. Now remember, they're passive. I can see that depending on their position, the frequency of oscillation changes. So blue is one of them and red is the other one. And so you can see that in the top two, the frequencies are very similar. But in the bottom one, if I put them in those two positions, their frequency of oscillation is different. So there has to be some communication between all of the posts, and that's setting up the frequency of oscillation. So before we looked at when we had one active and one passive. But you can have two active. So this is catalase and this is urease. And I think this will show you how you can create these systems that are not symmetric. So the catalase is right there, and it's generating inward flow. So it's a pusher. But then at the same time, because I'm going to put urease and catalase, urea and hydrogen peroxide at the same time into the box. So at the same time, urease is generating outward flow. And so the sum of these interactions looks like the picture in the middle, near the bottom. And so that, and here's another example then, even though they're both active, one moves and the other doesn't. So they're both active, but I can just get oscillatory behavior in one. So again, there are design rules. We know how to put them together to get the desired behavior. So I think this is the last one. I just want to show you that if you have one active one and you add a lot more passive ones, they still communicate. You can see that because their frequency of oscillation at P1 is one location, P2 is another, P3 is another. They're labeled here on the right. The frequency of oscillation of those posts are not the same. So there is this communication through the fluid is transmitting a separate message to each of these that's dictating their motion. So let me tell you what I told you. We looked at mobile objects and we found that we could use buoyancy and diffusioosmosis to put these structures together. And buoyancy and diffusioosmosis are driven by different things. So I can have them be directed independently. And so it allows me to do this dynamic assembly or self-organization of different structures. And what's kind of cute is when all the reactants are consumed, then the structure falls back to the separated pieces. So this self-assembly is reversible. And for immobile objects, then I showed you that the addition of reactants leaves these fingerprints. And the fingerprints are unique because they depend on so many parameters, but mostly because of that pseudo-buoyancy coefficient, which is unique for each chemistry. And I also showed you about the kaleidoscopic effect. And so this allows for standalone sensors. So the idea is that because of the pattern it forms, it can tell you what chemistry is going on. And it allows for rational design of surface topologies. And the notion of a sensor and telling you what chemistries are present, my group doesn't do this, but you can imagine that you might be able to apply machine learning. That is, you know what reactants you put in, you've got a particular pattern. And so you build these correlation tables about what combination of chemicals gives you a pattern that's like that or very similar to that. And with that, I thank you very much for your attention, and I'll be happy to answer questions.
Thank you so much.
Thank you. Thank you.
Does anyone have any questions? We'll open the floor. Tad.
Now, this is a really interesting mix of the fluid flow and the chemistry. So thanks for that. So I just a couple of questions. One is, if you're thinking of extending this to smaller scales, as I understand the Grashof number that you mentioned, it's a ratio of buoyancy to viscous forces.
Yes.
And generally, at small scales, viscous forces get more dominant. So would you need to have reactions that have a big volume change, like forming gas bubbles or something like that?
Absolutely. That's exactly right. And that's what's so nice about having these dimensionless numbers, that if you know that you're in the regime where the viscous flow dominates, then you're going to look around for chemicals that have a large pseudo-buoyancy coefficient. Yes, that's absolutely right. And that's the joy of working with Howard Stone. He expresses everything.
Yeah, well, that's one of the really good lessons of just fluid dynamics in general. You look at the dimensionless numbers, and then you can extrapolate to many different situations. And just my other one was, at the very end, you mentioned that the assembly can reverse after the reactants are consumed. I'm just was
Yes.
wondering, does that require making a good balance on these sticky reactions that you meant? That they're not
Absolutely.
too strong and not too light that you do that?
Absolutely. The forge can't be too hot or too cold. It has to be
Yeah.
just right. But in fact, in protein folding, that's exactly what happens, right? The bonding is not too strong and it's not too weak, so that you can quickly go from one configuration to another. So the kinds of bonds that can be readily made and broken are well known and can be well designed. So I don't think that's going to be so much of a limitation.
So that you could also, for instance, if you wanted to have assemblies that stayed assembled, you could just make those bonds stronger. Is that an option?
Totally.
Yeah.
Totally. Yes.
Yeah. Thank you. That's a really interesting technique.
Thank you.
Any other questions?
Okay.
Okay.
Well, if not, I thank you very much for your attention. And thank you, Lydia, for inviting me to give this fun talk. I always like it when there are fun things. Oh, there's somebody raised a hand.
Micah.
Yeah, sorry, I disconnected for just like 30 seconds, but I don't think you asked this question. Where do you see this tech going in the next 5 to 10 years? Like, what do you imagine people would use this for? Like, what are some kind of what do you dream about in the shower of this tech taking humanity?
Oh, I love it. Let's start with the immobile objects. What I can envision is if you have pollutants in your solution, then the pollutants might identify themselves through the pattern that you created. So the pollutants have a particular chemistry with the posts, and you get a particular pattern when that pollutant is present. So it could be a very nice sensor for water quality. And for the mobile objects, this is funny, but I want, if I could do this on a macroscopic scale, I mean, at really large scale, so that you can make portable shelters. I don't know if that's realistic. There's a new company that's building 3D printers that are making lightweight, flexible sheets, and they're going to use them to make these portable shelters. And so that's my dream. It's a vision that's far away. The vision for the bottom one, I think, is very doable now.
All
Can I
right.
have one more?
Great.
No, it's okay. No,
Sure.
so I noted on the animations where you're showing these assembling into a box that you mentioned the alignment that gets fixed as they come together. I was wondering, is that mainly
Yes.
due to the fluid flow, so they would align even if they weren't sticky, or is it mostly once they get close together, the stickiness pushes
It's
them in the
both.
right? Okay.
It's both. So I have both forces, the drag force, and then as it gets really close, this chemical attraction of the sticky forces.
But you have a lot of design space here, and that's really an interesting aspect of what you're looking at here.
Yeah, I think you've brought that to the fore, and I appreciate that. It's a very large design space. So what you have to do is come up with basic design rules and get the fundamental simple rules to work. And then you can start going on beyond that. But since you enjoy that so much, let me show you one other one where design rules were really important. So we had these simulations, they were done first, and there are two different types of enzymes on the same sheet. Because of that, you can have a promoter-inhibitor reaction. And that promoter-inhibitor reaction on the sheet makes it do this interesting motion. And then you might think, oh my God, that's weird. But then there were these experiments, and they showed exactly the same thing, except it's going the other way, because they put their inhibitor promoter in different positions. And it's the same thing here. We got it to do this lovely flying motion. And it's exactly what you see in the experiments. But again, they had the reactants coated on the bottom, so that's why it's doing that. And then finally, you can have stationary oscillations, which we had predicted. And in this experimental study, they do see the stationary oscillations as well. So the design space is a blessing because it just means your creativity limited. but it's also a bit of a curse because it's so big. And you want to make sure that what you predict can be actually realized.
Yeah, that's really interesting. Thank you.
I think Mika still has a question. I'll turn this off because it gets crazy looking after a while.
Yeah, I'm curious what the next bottleneck in scaling up is. Is it just an engineering problem and figuring out how to build things you want to build, or is there something like the viscosity versus buoyancy where there's some new component that comes into play that may be difficult to get over?
I think you've added a really beautiful question, and I think it's the latter. Now, you saw that the really beautiful thing about the Grasshopper number is it gives me a way to play. So if I want to increase the fluid velocity, and I increase the height of the chamber, because now that the chamber's taller, I can make these larger vortices. So if my assembly process is not adequate because the velocity is too slow, then I know how to play with that. I remember the little windmill I showed you, those were centimeter size. So knowing that number, and also the flexibility, the flexural rigidity. So what level force, what kind of flexibility do you need to be affected by this force? So given the wonder of dimensionless numbers, I think you could resolve some of those problems, but and then it gets to the point where it really is a fabrication issue. So I tried to show you that the system was very fault tolerant, but if you're going to do this on a larger scale and you're spraying enzymes onto a sheet, coating's not uniform. So yes, I think scaling up is a wonderful idea. And
so if I understand that correctly, you think the kind of the next hard problem is going to scale up to like meter scale, let's say, would be figuring out ways to reliably get those sheets, generated at the volumes that you need. Like we need meters of sheets,
absolutely.
not just millimeters. Okay.
The sheets to be the right flexibility, to get the coating fairly uniform, to get the velocity be in range where, it's sufficiently high that it can. But all of those things, the velocity, what you need, I can predict the flexural rigidity that you need. And I showed you that you have some fault tolerance, but probably not on the house panels on the house.
We'll get there eventually. I like your.
Anyone else? Oh, I think the computer thought that I was raising my hand. Okay. Well, I think this is the last Molecular Machines seminar of the year. So we'll see you all in the new year. And thank you, Anna, again for coming on and giving a great presentation. It was so lovely.
Thank you. It was really fun. Thank you. Bye.
Yeah, thank you.
See you soon, everyone.
Bye.